All right. So we left off yesterday talking about the ramp, and we decided that, or we discovered that if a block falls off the bottom of the ramp, 5 meters, it hits the ground with a speed of 10 meters per second. Yep. It falls for 1 second. And I asked you, I asked you what would the velocity be if it slid all the way down the ramp. So let me fix the graphics before we go any further. Alright, so then I asked you what would be the velocity if it slid down the ramp, and let's say our options are less than 10 meters per second, 10 meters per second, or greater than 10 meters per second. Have you decided your answer? Okay, so basically we decided that if it falls over the back, it's going to hit the ground at 10 meters per second. And my question to you is, what if it slides down the ramp without any kind of friction? If you believe it's going to be less than 10 meters per second, raise your hand. 1, 2. Okay. If you believe it's going to be 10 meters per second, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. If you believe it's going to be more than 10 meters per second, raise your hand. 1. So like 5 or 6 of you are like, I'm not even going to guess. Too shy. Turns out it's going to be 10. Ignoring friction, the change in potential energy should be the same. So if you're going to fall from that height on either side, you have a change in potential energy, and hopefully that change in potential energy and the change in kinetic energy is going to be the same regardless of how you got there. Now, huge caveat, ignoring friction. If you ignore friction, then yeah, it's definitely going to go the same speed. If there is friction, then you have an issue where it's going to slow down. Now, what about the time to get there? What about the time to get there? So we learned that if something falls 5 meters, it's going to take t equals 1 second to fall all 5 meters. What about the time to get down there? Is it going to be t equals 1 second? Is it going to be greater than 1 second? Or is it going to be less than 1 second? So why don't you think about that for a little bit? So I just told you that the velocity at the bottom is still going to be the same 10 meters per second. But what about how long it takes to fall? Will it take to slide down? Will it slide down in 1 second? Will it slide down in more than 1 second? Or will it slide down in less than 1 second? So take a couple seconds and chat with your neighbor, and then we'll decide. Sure.
Is it the same distance?
Yeah, I know, right? Right, it would be accelerating because there's no friction.
No, because it has the same ending velocity and it's going farther. It's going to take more time.
All right. So who believes that the block without any friction will slide down to the bottom and get there in 1 second? 1 second? None. Who believes it's going to take more than 1 second? Pretty much all of you. And you're right. Yeah, it's going to take more than 1 second. And it's because if the block just falls, it's going to fall with an acceleration of what? Yeah, 10 meters per second squared. But we also learned the force dragging down the plane is equal to force parallel, and that force parallel is Fg sine theta with whatever that theta is. Okay? So this is going to fall with Fg over m, and this is going to fall with F parallel over m. Does that make sense? So it's going to accelerate according to weight divided by mass. Down the plane, it's going to accelerate according to F parallel over mass. So F parallel over mass is Fg sine theta over mass. So yeah, there's that sine theta that makes its acceleration less, unless the theta is 90, and then in which case they're the same. So it's 90. Okay, so yeah, lesser acceleration, it's going to take longer. Okay. Give me a thumbs up if that makes sense. All right, cool. So again, what is the change in potential energy if the block falls to the left edge? What's the change in potential energy? MGH. So the delta PE is MGH, and the M is 4, the G is 10, and the H is 5. So we decided yesterday with 200 joules.
Yes.
Okay. And then, what's the change in potential energy if it slides down the ramp?
200 joules.
Same 200 joules. Same 200 joules. Because the change in potential energy is the same. So the height from which it starts to the height at which it ends is the same. So since the m is the same, the block is the same mass, the g is the same, and the height is the same, it'll have the same change in potential energy. Because it falls 5 meters there, it also falls 5 meters when it slides.
So what if the ramp didn't fully end where the other one
If the height were different, the potential energy would also be different. What is the kinetic energy if the block slides down the ramp? 200, yeah. Because again, if there's no friction, then whatever potential energy it has at the top of our reference point, or top of the ramp, it'll have the bottom of our reference point. 200 joules of potential becomes 200 joules of kinetic. And lastly, what is the speed if it slides down? We calculated that to be our 10 meters per second. Okay. Right. Next, finally, I ran out of space, so I put it up here. How much work is done if the block falls off the bottom of the ramp, or the back of the ramp? How much work is done?
0 because it's not in the same direction.
Not 0.
Dang it!
So again, work, it's all right. Work is force times distance. Work is force times distance, right?
Yes.
This is important. I'm going to erase everything else except for what is relevant.
So you use FG.
There we go. The rest is relevant. And actually, FG is relevant too. FG is relevant. Okay. So if the block falls off the back of the ramp, how much work is done? 200 joules.
Oh, I said.
So work, we can look at this two different ways, actually multiple different ways. Work is the change in potential energy, because the potential energy becomes kinetic energy, right?
Yeah.
So all the potential energy becomes kinetic energy, so the change in potential energy is negative 200 joules. Well, it's also the change in kinetic energy, and the change in kinetic energy is positive 200 joules. So it's 200 joules either way. Okay, so work is the change in energy. It's also the force times the distance. What is the force that's dragging the block over the back, or dragging the block down after it falls off the back of the plane? Gravity. Fg. And so Fg times d. What is the Fg of the block? The weight is 40 newtons. Because it's a 4 kilogram block, it's 40 newtons of weight, and how far does it fall? 5 meters.
Which is 200.
Which is 200, exactly. Make sense so far? Okay, yes?
If you found the potential energy, could you essentially already have work
Yeah.
instead of trying to convert it?
Yeah, absolutely. If you understood what work is, then you can say, well, if there's no friction, all the potential energy becomes all the work. Because all the potential energy becomes 0, all the kinetic energy goes from 0 to 200, so the work has to be 200. Okay. Who does the work in this case? Gravity does the work. Yeah, gravity does the work. So we would say there was 200 joules of work done on the block. Done on the block by gravity. Okay, does that make sense so far? Okay, so let's extend our understanding. What's the angle? Just throw out a number.
4.
30 again. 4. Yeah. 30 degrees. Okay, so we love 30 degrees. 30 degrees is fun because it has to be 0.5. So if it's 30 degrees, then the force parallel that drags it down the plane is Fg sine theta. And we decided the Fg is how much? 40 newtons. And sine 30 is, yeah, so sine 30, oops, I'm going to put 30 in there, is 1/2. I'm going to put 30 in there. So the F parallel is 20 newtons. Cool? Cool. Now, how long is this hypotenuse? We're going to call this d hypo. How long is d hypo?
14.
It's 14? Okay, so Taylor did the math for us ahead of time, thank goodness. So that means the work done down the plane will be force parallel times d hypo. which would be 20 times 14.
No. I
Yeah.
was just throwing out.
Oh, okay. It's like, thank goodness. Like, physics broke. So if the height is 5
I'm sorry.
and this angle is 30, then the hypotenuse must be what?
The distance.
10. Yeah. Are you doing that because you realize this has to work, or you're doing that because the trigonometry works?
Because it has to be
Because that's what it is.
Yeah, 'cause it has to be 200. It's like, I know it has to be 200 joules, so this has to be 10. And yeah, it is 10. If this is a 30, if this is 30, then it has to be 5, 10, and this would have to be, I don't know, 8.6, I guess.
Yeah.
Distance of the hypotenuse.
But sometimes
So if it slides down the hypotenuse, whatever work we had falling is going to be the same work as it fell over if there's no friction.
I'm sure.
But the forces aren't different. Now this is important because if you're going to move a dresser into a moving van, do you want to just lift it up,
No.
or do you want to slide it up a ramp?
slide up and
Yeah, slide it up a ramp. If you slide it up a ramp, you have to apply less force over a longer distance. But the overall change in potential energy of the dresser is the same regardless if you pick it up or slide it up the ramp. The overall change in potential energy. Just like if you reverse this process, the overall change in potential energy is the same whether you push the block up the ramp with F parallel multiplied by D hypotenuse, or if you picked up the block multiplying, basically applying an FG over 5 meters. The overall change in work should be the same, ignoring friction. Always ignoring friction. Okay, questions?
it's kind of
Give me a thumbs up if this makes sense to you. Okay, come on, friction. How come you always ignore friction? All right, so here's one with actual numbers. Do we even need to do this? I do not believe we do.
All right.
I think we've done everything we need to do with ramps and blocks, so let's just skip it.
Okay.
All right, next. Potential energy of a compressed spring. If you aim a Nerf dart at a friend's face and you pull the trigger, they're like, ow, you hit me with a Nerf dart. And you're like, no, the spring hit you with a Nerf dart. Because the spring had a lot of potential energy stored up. And that's how it works. So you can store gravitational potential energy in an object. So by lifting this up, I've stored potential energy into it in the gravitational form of potential energy. But I can also get a spring-loaded device and fire an object that has stored potential energy in a spring. Okay, does that make sense? All right. Now before I get to it, we have to talk about something called Hooke's Law. This guy named Hooke, he had this crazy idea that if you push on a spring, a normal spring, the amount of force it takes to compress it is equal to what's it called, the compression constant or the spring constant multiplied by how far you compress it. Which should make sense. You've all pressed on springs. It's easiest to press it when you first get it going, and harder as it keeps going. So if you get a hard, like in my Slinky here, it's very easy to just pull like this. But as you pull and pull and pull and pull, you have to apply a little bit more force after it's been extended quite a bit. And the more you extend it, the more force you have to apply. So that's Hooke's law. The negative is there because Hooke's law the spring force tends to act as a normal force. So we throw a negative in there. You don't always see that negative. In fact, I've seen probably about a third of textbooks drop the negative. So you don't need it there, it doesn't need to be there. Okay, so let's graph Hooke's law. This used to be a lab I used to do before I realized it was such an obvious, wow, then I can make a straight line. Before I realized it was such an obvious principle that we didn't have to actually investigate it. So if you graph the force you must apply over x, by the way, x is displacement. I don't know why it's not d, it's x for some reason. Then what would this graph look like? Yeah, show me with your hands what the graph would look like. Would it be a horizontal line, a vertical line, a diagonal line? Would it be curvy one way or the other? What would it look like? Yeah, most of you got it. It'd be diagonal line, right? Yeah. So it would just be a diagonal line like that. And the slope of this line would be what?
Would be
So,
F over X.
would be k. Yeah. The slope would just be k.
Dang it.
Now, again, if you went the other way, it'd be negative k, but again, this is part of the reason why a lot of textbooks will drop the negative. So yeah, so if y equals mx, y equals mx, y is f, m is x, and then k, m is k. So m is just a slope. So x is just x, and m is a slope. Okay, does that idea make sense? So if you're compressing a spring, what it means is the compression force you have to use increases as you compress it away from what's called the equilibrium point. Or if you're pulling on a spring, the force you have to use increases as you pull it away from what we call the equilibrium point. Equilibrium point where it's like unstretched. So for instance, if you had a slinky like this, that's the equilibrium point. I pull it away from the equilibrium point, I have to exert force on it. That's Hooke's law. Now why is that important? Well, energy stored in a compressed spring is simply the work done on the spring. The more work you do on the spring, the more compression, the more energy is stored in that spring. So, what is W? Work. What is F? Force. What is D? Distance or displacement. So if you put these two equations together, what you get is work equals force times distance, and force is kx times distance, but x and d are both displacement. So the work done on a spring is kx squared. Almost. Almost kx squared. There's something missing. You will. So Hooke's law is force equals kx. Now energy is force times x. Force is kx. So if we drew a graph of work times displacement, you get something kind of interesting. The graph looks like that. It's exponential because of the square. But here's the thing. The force you have to apply is not a constant force. Does that make sense? The force you have to apply is not a constant force. It constantly increases. So what we have to do to find the work is we have to take the area under the curve. And this looks like a triangle. A triangle is 1/2 base height. So the energy stored in a spring is 1/2 kx squared. 1/2 kx squared. Since the work you have to apply is force times distance, and the energy you have to apply is the work, force times distance, and the force is not constant, the force increases over distance, you have to use the area under the curve, and this becomes 1/2 kx squared. In other words, this is kx times x, but since it's a straight line, it's kx times x 1/2. This is work equals 1/2 kx times x. That is that. Okay, how are we doing so far? Okay. And over your head? Okay, we're good. We'll go over it again. So we're ignoring friction, of course. We're ignoring friction, of course. So what this basically means is, practically speaking, if you are pushing on a spring, you have to exert more force as you push it further and further from its equilibrium point. The more you stretch it, the more force you have to apply. So far, so good?
Yeah.
And work is force multiplied by distance. So the more you push, the greater force you have to apply over the distance you have to apply. So you have two x's. You have k and x, which is the force. The more you push it, the more force you have to apply. K is constant. So the more you push it, the more force you have to apply, and the more force, the force you apply times the distance is the work. So this becomes W equals kx times d, which is effectively kx squared. But since it's not a constant force, since the force starts small and becomes large, you basically have to take an average force. That's where the 1/2 comes in. So down here, you're applying a very small force. Up here, you're applying a very large force. So you have to use an average force. That's where the 1/2 comes from. It's 1/2 kx squared. So what this means is, if you have to apply a force on a spring, you get the spring constant, multiplied by how far you have to push it, multiplied by 1/2, that is the potential energy. So, let's look at the situation. A block on a spring, a block is going to fall into a spring. The spring has a constant of 200. I'm not going to worry about the units, just call it 200. And compresses a 2 kilogram mass, dropped from 1 meter above. So, how much would it compress it if you had a 2 kilogram mass dropped onto a spring from 1 meter above? So this is 1 meter, this is 2 kilograms, and the spring is going to compress a distance x. Is this something we can figure out?
Yeah.
Yeah. Because we can say, well, the spring is going to have potential energy spring, and that change of potential energy spring is going to equal what?
1/2 kx squared.
Yes, but practically speaking, it's going to equal what?
FD. K,
Yes.
K, work.
Yes. The potential energy of the block, right? So it will actually, we can actually say equals KE equals the PE gravitational. So whatever gravitational potential energy the spring has, or the block has here, it's going to fall, it's going to turn into kinetic, it's going to arrest all of its potential and kinetic energy, and all that energy is going to be stored in the spring. So can you do that? Is that, with the numbers you have, is that something you can do?
Not alone.
Well, let's walk through it. So potential energy spring is 1/2 kx squared, and potential energy gravitational is mgh. So do we have m? We do. Do we have g? Of course we do. Do we have h?
No.
1 meter above the spring, we have h. 1/2 is just a number. Do we have k? K is 200, and x is what we're solving for. So using this information, we can solve for how much would the spring compress. Yes. And
What is the second word under change of PE?
spring, grav,
Grab?
yeah, gravitational. Gravitational potential energy and spring potential energy, sometimes called elastic potential energy. I really don't care which one you choose. I hope they have ice cream bars for you guys on all your straight O's.
I hope so too. I never used
I wish I could have.
I'll give you mine. Me too.
Aww.
I
I'll be in here watching
always-
Netflix doing my
Mr. E gave me an S. He ruined it for me.
Someone gave you an S? You're not an S student. You're not satisfactory. You're outstanding.
I got all. Look, you got an S. Mr. E, he was like a student
What
teacher
mean?
from Miss
What
Murphy.
mean man hurt you?
It's okay. We
I
love
love
it.
it.
Oh, it's amazing.
He was so good.
27%
He was
was
such a good man.
He was amazing.
He didn't give everyone O's just because he
Yeah, I used to do that. I used to be like, you have to be outstanding to get an O. And I'm like, I'm going to compare you to the kids I had in the valley. All right, so K is what you're or X is what you're solving for. So if you like to do math and like to put things in crazy equations, this becomes the square root of mgh over 1/2 K. If you like to do that. If you don't, if you're like me, you like to do separate steps. And the answer's going to be the same either way. How much is the compression? Point how much? 0.44? 0.45?
Yeah.
Okay, 0.45 meters. That makes sense to me. That sounds good. Okay. I didn't actually do it in my head, but let's see. If this was 2 by 1 by 10, that's 20, right?
Yeah.
And then 20 divided by a half is 40. 40 divided by 200 is 0.1/5.
Yeah.
Yeah.
So this is square root of 1/5. This is
Yeah.
about half. That sounds about right. Yeah. Okay. Cool. Okay. So what this means is, if you had a spring, with a compression of 200. 200 is a pretty good spring. That's like a shock on a bicycle. Took a 200 spring and you dropped a 2 kilogram mass onto it. And if you dropped a 2 kilogram mass on it for 1 meter above, it would go boing. But something interesting would happen. It would go boingy, 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 until it settled at a certain distance. Okay. So to give you an idea, so you can actually see what's going on. Imagine you had a spring that can stretch quite a bit. In fact, this thing can stretch a lot. And you dropped a 2 kilogram mass on it for 1 meter above, it would go pew, boing.